So, it's all done. Let's go have a beer. I put this up first just to tell everybody I'm going to be deep diving under the covers, but DPDK on Azure is generally available today. It's supported on the VMs that you get in production in Azure. You don't have to be some special sign-up. And if you use the latest enterprise distributions, we've worked with the partners to make sure that all the DPDK libraries they have the right versions. And we've got many partners in various stages of porting their DPDK applications to Azure. I would like to announce ones that are done, but they haven't told me, and I don't know of any right now. So what I'm going to cover in this talk is why is Azure networking different? How is it different? And what you need to know about what's going on under the covers, and what you should do in handling drivers, versions, and what's going on. So the basic problem is in the cloud world, networking is slightly different. We have two requirements that are really demanding. The first one is high performance. Everybody wants the maximum network performance out of these fast machines they've got. We also require cloud security, where you don't want other people to be able to steal your credit card numbers, your information from what's on the network or from what's being run on other guests on the same VM. And I went looking for high performance and secure cars, and I came up with the Batmobile. So how does Azure networking work today? We have a custom FPGA. I should use my magic pointer. And the FPGA is the core which does the acceleration. So it has a flow table, which is programmed. It does all the QoS, and it manages the overlay networking. And that acts as a bump in the wire in front of a NIC, which we use as a virtual switch. And we use the 40 gig Mellanox today as the switch. So packets come in from the top of rack, go through the FPGA, go into the NIC, and then get fanned out to the guests. And how does this show up in the guest? Traditionally, on Hyper-V, networks went through virtual switches. And with accelerated networking, we give a VF to each guest. So each guest can see their own slice. That gives them line rate performance. But we also have a fallback path. And the fallback path is a synthetic network that's been around in Hyper-V for years. And this is how we present that to you in Linux. We present it with a Netvsc device, which is ETH0, and a PCI device, which Mellanox driver with ConnectX-3, that both are merged in the Netvsc device and set up the stack. In DPDK, the current DPDK on Azure, it's done in a more complicated manner, but that's because the DPDK provides a different set of primitives and is more complicated. So we have the same underlying VF, the same underlying synthetic device. We use the kernel to do the synthetic networking and then use the tap device to get those synthetic packets up into DPDK, and the SRV path goes through the Mellanox InfiniBand RDMA verbs and the PMD, and the Failsafe PMD is what unifies those two into the DPDK application. I should talk a little bit here about the two paths. The synthetic path is used for the first packet in the flow. How many people in this room know what OpenFlow is? So in OpenFlow, traditionally, the first packet goes through an exception path, goes into Userspace. Userspace decides what it's going to do with it, and then programs the hardware to do with the rest of it. We do the similar kind of thing, only we're programming the FPGA. So the hypervisor takes care of all that. And once it's programmed it through the FPGA,
it comes through the VF path. So the first packet is going to show up on the synthetic path. The rest of the packets the guard has stamped them at the door, give them the VLAN tag. It's going to go through all the right path, the high-speed path. And this is what's shipped today. This is what's announced. This is what everybody supports. There was previously, and I ported over, a Netvsc PMD driver, which was working totally in the DPDK with a very small shim and UIO. For 1811, I proposed a transparent VF mode where Netvsc PMD driver takes care of all that fail and tap path and provides a transparent way for the Netvsc PMD to get into. And in the DPDK application, only sees one device. So why bother with the Netvsc PMD driver? We have something that works today in Azure. Well, the Netvsc PMD driver works with or without SRV. So if you were doing on-prem and you didn't have, which is just basic Hyper-V, and you didn't have SRV, and you wanted a solution, Netvsc PMD works. And I've got a couple of people I'm working with, working on applications that way. It's a lot less overhead. It doesn't have all the tap and the copies and everything else going on. And it's smaller. It's about a third the size of the code. And it's a lot simpler path. So there's less CPU cycles spent going through there. In order to do that, it needs a UIO driver because you can't magically have hardware appear in Userspace. You need a kernel component to make that show up. The original version of this driver, back when it was done by Viata Brocade, kind of glommed onto the kernel driver. And I ripped that all apart and went back to, well, how does UIO work? What's the UI model in the kernel? And there's a set of resources that the Userspace needs. So what is that in the VMBus world? It's you have a transmit and receive ring, which is one memory area. You have a monitor and interrupt page, which is basically, if you want to send something, for example, you put it in the transmit buffer, you put a descriptor in the transmit ring, and you go poke the host saying, I got something for you. It's in the mailbox. Those yellow ones in the mailbox. And there's a transmit and receive area. So data that comes in gets deposited in the receive area, and the descriptor in the receive ring is updated. The Netvsc PMD driver also supports multiple channels or multiple queues. So the way that works is the Netvsc PMD driver asks to have a new queue created. That comes in on a control channel, which the kernel is the only one who sees it. And a callback happens in UIO that basically sets up another sysfs for the separate rings for the subchannel. One other thing about this is the receive area I use. Remember earlier they talked about external MBUFs? So I went ahead and used that external MBUF API so that small packets get copied into fresh MBUFs, but anything big, if you're doing real data transfers, the MBUF is created and it points to the receive buffer in the receive area. So it's optimized for large packet receives, and small packets we have to copy it out of the receive area. The transmit buffer is something that's on VMBus specific, and it's a way to optimize transfers. Turns out that setting up the DMA in the host is moderately expensive because it has to go lock down pages and do stuff. So if it has a predefined area that's reserved, it's faster to send from that. So that's both of these or all these are fairly large. Like the transmit and receive buffer are 16 meg, and the default receive and transmit rings are 4 meg. So the reason that is true is because there's latency going from the guest to the host, and you need a bigger buffering to improve that. There are 2 drivers now. There's the one that's out there that's available today, the Failsafe,
tap model and the Netvsc PMD, and I wanted to highlight some of the differences. Failsafe is there, it's stable today. It only requires kernel 4.2. It's been around since DPDK 1802. It's the version we recommend, or later. It's supported by all the enterprise distros. It uses a bifurcated model, which means that the network devices show up both in the kernel and in DPDK. And to use the failsafe model requires SIRV. So basically it only works if you have the device pass through. Now, it doesn't need that device has to be active. For example, to do maintenance, it's quite common that briefly we'll take the VF away from the device, from the guest. We'll do maintenance like update the Mellanox firmware on the host, and then we'll bring the VF back to the guest. So even though we don't actually do involuntary live migration, we will do maintenance windows where, which we call VMBus, but basically where we bring the device offline and back online to the guest. The Netvsc PMD driver is experimental. To really use it well, you need kernel 4.18 or later. To use it well, you need DPDK 1811, because that's where the VF support is. And it uses a device assignment model. So if you're familiar with the DPDK and you're using Intel cards or pretty much anybody else but Mellanox, you take the device, you rip it away from the kernel, and you give it to a driver, either VFIO PCI or IGB UIO. In this case, you give it to the HV UIO generic. So you're basically assigning the device to be a DPDK device. And the Netvsc PMD driver works either with the vSwitch or with the vSwitch and SRV. The roadmap for this. So last year I was here, and this is pretty much what I said would happen. We had a preview version. We had one version of Ubuntu that had it, and you could make it work with 1711. So in preview 2018, it's on by default. AN means accelerated networking, basically VF support. It's supported in every distro on the planet pretty much that supports accelerated networking. Needs 1802, and with the Netvsc PMD, there's an early version in 1808, and the version that supports accelerated networking I proposed, and it's heading for 1811. So this is probably what you care about, which was why the performance. Turns out that with accelerated networking, you get a 40 gig network, but it's capped at 25 gig. So, and the reason why we do that is there may be one or more guests. We don't want to basically let one guest saturate DDoS the switch. So here's my test, but this was not done. This was done on my box, not on Azure. Transmit only, single queue, and it was on my little Xeon, which these aren't the flavors of Intel chips that are in Azure. So the numbers will be different, probably better. So with my 40 gig switch, I was able to get, with SRV, over 16 million packets a second out of test PMD going out. So that's the number, and you can easily hit the cap of 25 gigabits a second with DPDK or with Linux, and you can hit the packet maximum of the VF with the DPDK. If I used direct assignment, this was the other possibility. This is Windows Server. I had a 10 gig Intel NIC. I direct device assigned it, so the PF is showing up in the guest, and it was hitting about 8 million packets a second. That's about what you would see on bare metal for that particular hardware with a single queue. You get down here just to show you the dramatic drop-off. This is tap at Netvsc. You're down about 600 to 800K packets a second going through the synthetic path. And that's fundamentally limited by the fact that every packet has to be processed by the vSwitch and the Hyper-V. So you're basically hitting the limit of Hyper-V software packet processing. So all this is done. My life is easy. I should be able to go home. Well, the real world is full of people wanting backports. They want something new in the old. So people want to run all this on older versions of DPDK. Nothing's impossible. I just like to tell people what's the Netvsc PMD driver needs the bus infrastructure that was basically introduced in 1711 to even get started. The Failsafe and all its friends needs the VDEV and a lot of the other things that were in 1711. And there's the VDEV Netvsc, which does all the configuration. It really needs the DevArv stuff from 1802. So if you're going to backport stuff, you're going to carry a lot of baggage back with you. And the farther back you go, the more you're going to have to backport. So, and OS support. There is a certain amount of kernel stuff that, even though it's not large in volume, has to be backported as well. So if you're using the Netvsc PMD driver, you obviously need the UIO support. There was an early version put in 4.14, but it doesn't have enough to be useful. So minimum, you need 4.16 to get a single queue to work, and you need 4.18 to get multiple queues to work. That's just because I don't have precognizance. I don't know what I'm going to need till I build it. But the good news is that's contained. That's basically a single driver you have to backport. You don't have to backport the whole network subsystem or anything special. To support the fail-safe, the current model, and the tap device, you need eBPF and the classifier, and you need some of the RSS classification. So it goes to 4.2 and 4.9. So you'll need to backport that as far back. I mean, we have people asking for things on 3.16, okay? So we also have people asking for FreeBSD support. We do support accelerated networking on FreeBSD, just not the DPDK side. First thing, obviously, is the tap device on FreeBSD is different than the tap device on Linux. So you either have to change the DPDK tap support to work with the FreeBSD version, or make the tap device on FreeBSD support multiple queues. So that's if you wanted to do the UIO and the Netvsc, you obviously have to have a UIO driver that works on FreeBSD. And the UIO model on BSD is different than the UIO model on Linux. So that would be backporting. So what's the future? Well, first of all, I'm not investing significant effort on my own to push Netvsc PMD driver or any new features into this. What I am going to do is respond to requests people have, what they're interested in. So these are ideas. These are not commitments. First off, the performance of the Netvsc PMD driver could probably be boosted by 50% by just some simple optimizations of not copying things in and out of the ring and aligning things. All the work that's been done for years on VirtIO. I mean, you could even go to the extreme of SSE instructions if you wanted to. The offloads, the Netvsc PMD driver, and even the failsafe do not provide as many offloads as available in the underlying hardware. So we could pass through some of those. But it really comes down to how much of the DPDK and the hardware side you want to re-implement in software to support the synthetic path. So flows, simple things like RSS parameters you could probably do where you give the same parameters to both devices. But there's a lot more richness in the DPDK, and the fact that you've got two sides, how much you want to support. And one could even argue, can you figure out a way to do that generically for bonding and failsafe as well? FreeBSD support is not currently funded or planned, But if somebody comes and does it or wants to talk to me about how to do it, that would be great. ARM support is not actually funded or planned, but you've seen that there's Hyper-V ARM support patches for the Linux kernel that just went out. So it is possible, it's just not anywhere on the roadmap. I also wanted to, I put this slide up last year, it actually got bigger. A whole lot of people did a lot of effort to make this happen. It wasn't just, I mean, we actually considered that a value at Microsoft, that collaboration and getting multiple people to work on something is good. And the names and the number of different areas that have contributed is really huge. We've even got testing in multiple companies, and I can't even put up the partners that are now involved because they're not there. With that, I think my time is officially up, and I've got some time left for questions. Yes, back there. You're in front of me.
There was a block in one of your early slides about RDMA, and
yeah.
I know that when we've had to, port this driver, like the forward port we did for 1805, there's a lot of InfiniBand that goes in there. There's a lot of stuff to drag along. Is there any plan or option to reduce that?
That's a function of the Mellanox driver. And I would talk to the people from Mellanox. They've done a lot of work to actually get from requiring the out-of-tree OFED drivers and requiring out-of-tree whatever to getting down to using the RDMA core and the upstream drivers. So I think they've done a lot of great work to get that reduced. Once again, though, it's a case of it's easy to go with the today. It's hard when you go with the backports because you get into the...
Yes. So I have two questions. First of all, regarding the external buffer, one of the items, I don't know if you handled it nicely or not, if you commit to this external buffer, if it's a huge or a big packet that arrived, what if the application doesn't release it?
I actually did kind of the same thing. Okay, lazy, I always cloned somebody else's implementation. I looked at the one real user of the external buffer, which is in the Mellanox code today, and I did the same kind of thing, which says, I will go and make the decision in the driver of whether or not to use the external buffer based on the packet size and the number of outstanding external buffers. Okay. So if there's more than half the area has been used up with things, a copy happens. So it's transparent, that won't live lock itself. Okay. But at some point, you will see a performance roll-off if you've got a really slow reader.
And second question, how do you explain to the users which kind of PMD to use? If to go with a Failsafe or to go with a new Netvsc PMD?
We're saying go with Failsafe today. It's only new development or people that are, wanting to be early access or had requirements to use the Netvsc PMD. Eventually, we'll cut over, but I'm not really ready to say, go for it now.
Okay, do you support multiple processes?
Yeah.
Okay, so just accessing multiple queues on the Netvsc.
And it turns out you can have both at the same time because, for example, one is device assignment. So if you give a device over to HVUIO, it gets picked up by the DPDK application as Netvsc PMD. If you don't give that device over, then VDEV Netvsc makes a decision based on whether or not it's being used by the kernel or not. So you could actually have both at the same time.
Okay, thanks.
Back there in the back, I see somebody.
Hi. I don't know if you can disclose this, but so you compare your implementation with OVS.
Yeah.
So I'd like to understand what's your flow definition and how many flows you have. Like, is a flow up to layer 4, above, below? How many flows do you
it's
see?
basically invisible to the guest, but it's done on the host side, and it's done on layer 4 data.
So up to layer 4 for the user traffic.
Yeah.
And if you have 1 million of flow, how does your implementation behave? With,
at some point, I don't know the exact numbers, and they've changed over time. You rolls over on the number of flows and it ends up falling back to, kicking up some older flows out to put newer flows in.
It's on the order of 500,000 to 1 million more flows per guest before it starts to be an issue.
Thanks.
Yeah, along the same lines, how many flow updates do you get in typical deployments?
That's impossible. It's like asking how big is a, I don't know. I mean,
Let me rephrase it. So are the number of flow updates, how do they affect your data plane? So imagine you go to, the reason why I'm asking is you end up in the hypervisor to go and process a flow update. Remaining packets that are coming in for the same flow, I imagine, get dropped. So that's why I'm...
No, basically, once the first packet comes in, what happens is basically in theory you could have multiple packets at the start of a flow, and they will take the slow path until the fast path is programmed.
Exactly.
So yes, you can have that happen, but it's only going to happen on a UDP flow where somebody's hammering you. A normal TCP flow, this three-way handshake will pretty much make sure that you program the response traffic before you respond. So it works well. I know our QA guys hammer on it, and the two ends of the spectrum are the ones where both the QA testing hits and the the performance corners are, one single flow, and the other one is millions of flows. I mean, single packet flows, yeah.
Thanks.
I have an easy question for you, Stephen. You talked about how pretty much every Linux distribution is supported now, and you remember probably painfully well the early days of Neil Horman coming in and trying to educate the community about how to get DPDK set up so it could be supported in Linux. Was the community work useful for you guys there, or were those two things kind of independent?
I think we were on the second stage where the community was already there and they already had packages. It's a question of making sure that their packages were updated by, that they had the right versions. And the bigger problem we have is like somebody wants RHEL 6 and they want a package on RHEL 6. And
okay, the backport story yet again.
Yeah.
Okay, thanks.
And the other one too is, somebody wants to support it with OVS and they can't figure out how to install OVS DPDK themselves. So you just moved one step up the ladder.
Great, thank you.
Thank you.
Thanks.